Okay, welcome to SQL Bits. We haven't done this in a few years, right? Live. So, welcome to the session that kind of broke the process. I'll show you later why. And we'll talk about the collations, encodings, weird characters, what characters are, etc. A little bit about myself. My name is Mladen Prajdic. I'm from a little country called Slovenia. If you're ever in the vicinity, let me know, we'll go grab a beer. I've been an MVP for like 13 years, 14 years now. I've been dealing with SQL Server for over 20 years. In my free time, I do a little add-in for SSMS called the SSMS Toolspec, and that's enough about me. This one's supposed to be the first one. So I still haven't seen this artwork creation. So I don't know why it messed up. I would love to see how it turned out. But if you have it, let me know. And this was supposed to be the next slide. So I usually start with this, and I ask, what is wrong with this picture? Right. So what information are we missing? So we have some binary code there, right? But we don't know how to read that binary code. Why? Because we don't know the mapping, right? We don't know how many zeros and ones convert to a specific character or a number or what they are. Are they like 4 or 2 or 1? We know by reading, like, because we have defined these things. But if we were to see an ancient writing, like, I don't know, the Egyptian writing, we didn't know the mapping and we couldn't read them. Right? Only with the Rosetta Stone we got the actual mappings. So what will we be talking about? We'll start with the basic building blocks of text, what they are. So I usually say the basic building block of text is a character. But what is a character? Right? It actually depends on your language, it depends on your culture. Right? It all started with ASCII, so basic Latin alphabet. One number equaled to one character. So this was the mapping, right? But again, it can mean different things to different people. If you take Latin A or Cyrillic A, those are two different characters. They sound the same, but they might have a different meaning, right? Then we get to code points. Then we dive deeper a bit. We get to code points, and a code point is basically an atomic unit of information, and text is a series of code points. Right? Then we go to a code unit, and that is an actual unit of storage for part of the code point, because code point can have multiple unit storages, multiple storage units. Right? So in UTF-8, that unit storage is 8 bits. For UTF-16, it's 16 bits. Right? So for example, if we take a letter X, that's one code point. It takes 1 byte in UTF-8. It takes 2 bytes in UTF-16. Right? If you have a euro sign or a pound sign, it's again one code point, but it's 3 bytes in UTF-8 and it's just 2 bytes in UTF-16. So again, it depends on what kind of data you have, right? A music note, if you're into music, a music note takes, again, one code point, but 4 bytes in UTF-8 and in UTF-16. And why is that? We'll look at later. Then we come to something called a grapheme. A grapheme is basically a sequence of code points presented as a single unit to us, to the viewer. So for example, if we take an A and an A, it's the same thing, right? But if you take an A with 2 dots on it, that can be a single code point. And then if you merge it through the Unicode rules, if you merge it with an A and just 2 dots on top, you merge those 2 code points into a single character, or a grapheme, it's again the same meaning, right? So we can have a grapheme built out of 1 code point or 2 code points or multiple code points. Then we get to glyphs. Glyphs are basically images that are stored in a font. It's the way we display the actual character. So in the end, what is a character, right? I usually say that it's the unit that gives us the most information, right? Okay, so then we get to collations. Who has, I mean, we've all worked with collations, right? Who has multi-language databases, for example? right? A lot of you, which is a good thing. I've been asking a similar question for 10 years, and 10 years ago, not a lot of hands went up. And then eventually, you most likely got a collation issue when comparing two character columns, right? And then you go in, oh, what are those collations? And then you open books online, or SQL Server help, and then you see this. It's rules for sorting case and accent sensitivity properties for your data. And then you're like, okay, fine, but what does that mean, right? So it basically specifies the bit pattern of text for each text, right? So how the zeros and ones are mapped into the visual representations of what we get. Right? So most relevant for us, usually, are collations that end with CS, so case sensitivity, AS, accent sensitivity, SC, supplementary characters, which we'll look at, UTF-8, bin, and bin2. Bin and bin2 are binary collations. So AS, accent sensitivity. What is an accent? And when is an accent not an accent? Right? We'll look at that in a demo. Bin and bin2 are both case sensitive and accent sensitive. Why? Because they compare text in their binary form, right? So we kind of skip the mapping part, right? Bin2 is the same as bin, but it's for Unicode, and it's fast. Right? It makes Unicode, it can do Unicode comparisons, binary representations of them. So let's look at that in a demo. Okay, so we're gonna use the simple AdventureWorks data. Okay, can you see, actually, why don't I see my, I'm gonna need some help here. Hey, excuse me, I'm gonna need some help. How do I, my demo is not showing. Yes, I have to cancel the PowerPoint. Okay, fine, sure, we'll do that. We'll do it like that. Okay, thanks. Yeah, all good. Can you see? Can everybody see? Yeah, back rows. Excellent, cool. Okay, so AdventureWorks. We'll do a simple text column in a table. I'm gonna have, because I'm from Slovenia, I'm gonna have a Slovenian collation. And I'm gonna insert some values in there, but you see there are kind of different characters in there. Some are accented, some are not. Some are maybe accents and some are maybe not. So if we search for all of the OPRs, how many rows are we gonna get? Any ideas? Just shout out a number, don't be shy. 1? 3. Exactly, 3, right? So, because we have case insensitive, accent insensitive, right, collations. So it doesn't care what the accent or case is. Okay, so what if we change that to this? How many now? You know there's a catch, right? I mean, there's like 4 values there, you know there's a catch. Still 3? Yeah. So why not 4? The last one has a different D. Yeah, so the last D, it's pronounced J, and it's not an accent, it's an actual letter by itself, right? So it's not counted as an accented letter, but it's its own letter. Right? So that's why case insensitivity here doesn't work. So what happens if you have an app, and I'm sure you have an app, that you would like to search through text, and you would like to downcast all of these things into their base kind of letters. So you would want to have the J go into D, for example, right? How would you do that? It's actually a very relatively difficult problem to solve because you have to do all of the replacements and then you have to do replacements on the text, etc. With collations, turns out it's relatively easy. Why? So you can use either a Cyrillic collation. I use a Cyrillic one because it's a completely different character set, right? Or you can use let in general one, it doesn't matter. But here, you see it returns 4 rows. Why? Because in Cyrillic, in the Cyrillic collation, the J letter is also kind of, it has a original base kind of representation that it can downcast if it doesn't know what to do with it. I don't know what it's officially called, so I just call it downcasting. I haven't been able to find the exact term of what it's called, but it works. So let's talk about variables. So I was going to ask what variable, what collation do the variables use, but the answer is written there. Right. So the variables, and this is actually really important, the variables used in your code use the database collation, and you cannot change that collation. Right. So if you do this, it won't work. I mean, it won't work as you expect it to work. So if I have like this, and I can see that my server collation is Slovenian, my database collation is SQL Latin 1 general, etc., etc. And my variable collation, so the C here, right, has the same collation as the database, even though I've specified collate Cyrillic, right? So the collate word, keyword doesn't work on variables, okay? It's actually a very important thing. This has bitten me a few times. Okay. So when we're searching for things, remember how I said that binary collations are faster than non-binary collations? So let's see how that works. If I say, come on mouse, I'm going to search for anchor, right? And in person address, this is how we usually search for this, right? I mean, we all agree, right? That this is how we search. This is the default search. But now, what if we can do this? If we say, okay, let's make it lowercase, because we are doing like with a percent sign in front, we cannot use an index, right? So we have to go through the whole table anyway, right? So if we have to, let's use this to our advantage. So we're gonna do lowercase anchor, and we're gonna have lower on the column itself, since we have to do it the whole table anyway, and we're going to collate it in a binary format. So we will skip all of the Unicode comparison and ordering rule and sorting rules, right? So let's see how this goes. Okay. And if you look, wait, did I do the two? Yeah, so the result sets are the same. They are actually the same. But the speed difference is quite a lot. It's basically versus, right? So it's 280 milliseconds versus 7 milliseconds. And if you look at the CPU time, it's 100 milliseconds to almost 0. So so this is basically your worst case scenario, right? And this is the best case scenario. Now, depending on how many searches you do, this can be a huge improvement to your process, right? Any questions so far? No? Okay. Let's move on. Yeah? Yeah? No? Okay. Okay, so collation sets. We have window collations. So basically, sorting is based on the actual Windows locale used, right? So the culture you use in Windows. It allows for the same sorting rules in applications and the database, right? Because you usually run them on Windows servers, this SQL server. In Linux, it's basically the same. Binary collations old binary collations define locale and code page, but it's legacy. The new ones just stored on Unicode code points. It's culture irrelevant, because Unicode spans all of these things. And SQL collations are basically just old school. They're used for compatibility with previous SQL versions only. But here's a little warning. If you use Azure SQL database, when you create it, the default database collation is SQL Latin. I don't know why this is, but it is. So you have to be careful about this. So collation levels, we have 3 collation levels basically. Server level. You set it at startup. It becomes default collation for all databases, including TempDB. So you have to be careful what your server collation is, because TempDB will have that collation. Changing it, no way. There is no way you're going to change it easily. Has anyone ever tried it? Yeah? Did it work? Yeah, exactly. Everyone is like, yeah, maybe. It depends on a lot of factors. I do not recommend it. I would rather just, detach the databases, reinstall SQL Server, or make a backup and restore. Then you have a database level, which you specify at the database creation time. If you change it, it doesn't affect existing data. It affects new data, so new columns, new inserted data. And column level. Basically, that's when you do an alter table. You specify alter column set collation. Those are main 3 collations. And then, of course, you have the query expression collations at the expression level, where you say collate at the end of order by or aware or whatever. Okay. Then we come to data types. We have basically 4 data types: char n, varchar n. What does the n stand for? I get various answers here. Any takers? The what? The maximum of what? Oh, national. No, this n, the char n, not the n char. In the parentheses. The size of what? The size of what? Yeah, exactly. Basically, it's the string size in bytes, or maximum number of characters. Because if you have 1 character for 1 byte, that's the maximum number of characters. But with Unicode, or with UTF-8 being introduced into the varchar data type, you can have less characters. You can have 1 character that takes up 3 bytes, for example. And we'll look at that. So code page encoding, 1 byte per character. UTF encoding, more than 1 byte per character. And for the n char, what does n mean? Some would say the same thing. It's not the same thing. It's the string size in byte pairs. Right? We all know this, but sometimes when you think about it, it's hard to explain sometimes. So what does n mean? National. We already somebody already answered that. Now, so national, nchar, and varchar, their base kind of encoding is the UCS2. And that UCS2 was basically 1 byte pair per character, so 2 bytes per character. UTF-16 is the subset. It can have more than 1 byte pair per character. Right? As we said, the music note, for example, had 2 bytes. Right? Okay. So now I have to cancel this again. Okay. So collation levels. I have a Greek database because they have a different writing. Again, we'll do the same thing. And here we're going to join to AdventureWorks, and it would help to create the actual data table. Okay. Okay. See, so this is what I was talking about earlier, right? We have a collation conflict, and the way to solve this is basically we have to say collate, and this will work. Never mind that it doesn't return anything. It's supposed to not to return anything. And the same thing is with the TempDB. Why? We said earlier. Exactly. TempDB has the same collation as the server, right? So that's why it's important. If you ever install SQL Server and you just click next, 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 next time, stop at the collation page and think about what you put there, right? Okay. Okay, Unicode. So first we had code pages, which was basically one-to-one mapping. This was in the 80s and the 90s. So 10 years ago, right? Yeah, I always say the 90s were 10 years ago. So it just means we're old. Windows NT introduced UTF-16 as its base encoding. So everything in the Windows NT and forward on the system level is encoded in UTF-16. So what is Unicode, basically? What is it? I mean, we talk about a lot of it, but what is it? It's an IT standard for consistent, that's an important part, consistent encoding, representation, and handling of text. It currently defines 144,000 characters, that's a lot, right? And it holds 159 modern and historic scripts and other input symbols. Now, I've put this on just to see, for you to realize the scope of it, right? How much stuff there is in there. And we still have a lot of places, a lot of space to have it, right? To add new stuff. So encoding is basically a way to translate bytes into meaning. So the first picture with the writings on the wall, we're missing encodings. So UTF-8, the subset of UTF-8 is ASCII. It can have 8, 16, 24, or 32 bits, so 1 to 4 bytes per character. UTF-16, 2 or 4 bytes per character. And subset is UCS2. UTF-32, it's always 4 bytes, 32 bits. But I haven't seen a system that uses UTF-32 for everything yet. Maybe in the future, right? Now, when we come to Unicode, we have something called planes. And I don't mean airplanes, but like planes of existence. It's very meta. So the plane 0, it's called a basic multilingual plane. And higher planes are called supplementary planes. And this is where the S_SC comes into play. It means supplementary characters. It means that our collation supports access to these supplementary planes, right? And there's 65,000 points per plane. And this is the basic multilingual plane. It contains all of the modern scripts of today and a lot of common symbols, which are not text. Unicode 1, so plane 1, is the supplementary multilingual plane. It's covered by those _SC collations. It has historic scripts except something called CJK, so Chinese, Japanese, and Korean historic scripts. It has field-specific symbols like music, maths, physics, biology, stuff like that. And then you get to real world. And you have a server and a client. And that's, in essence, that's what we have, right? A server and a client. And then you have a server that works in ASCII. And then you have a client that works in Unicode. And they talk to each other. And they don't understand each other. And the client says, OK, I'm going to send you some Chinese text here. And the server goes, I don't know. Cuts everything off in half and goes, yeah, I can do this. Right? So this is where you have to be careful about what your server collation basically is and what your client collation is. So best if you have Unicode, right? If you don't, you'll run into trouble. Trust me on that. I've been there, and it's not fun. It's not fun at all. Okay, so I have to cancel this again. Okay, so this is, I'll show you now the new Unicode stuff in SQL Server since 2019, pardon. Okay, so let's use the UTF-8 database. And note that this is a varchar. It's not an nvarchar, it's a varchar. So I have X, Unicode value X, byte count 1, char count 1. All normal so far, right? That's a normal X. There's no catch here. Those come later. Then we have strike through O, which I have no idea how to pronounce. See? If you have a multicultural audience, they help you. Now, Unicode value, fine. Byte count 2, but it's still 1 character, right? See? Then we get to or no, it's not A. Fine. Again, 2, 1. But then we get to the euro sign. Let me just do this. Now, euro sign takes 3 bytes in Unicode. But if you remember when we looked at the beginning, in UTF-16, how many bytes does it take? 2, right? So it's less. So depending on your data, you cannot just go, I'm going to turn everything to Unicode now, UTF-8, right? You have to know what kind of data you have, because if you have like a lot of characters within the 3-byte range, you'll actually increase your space. And then, of course, the music note has 4 bytes, and there's poop, which is also 4 bytes. I don't know, it's a joke. My son likes it. Now, for nvarchar, the things have been the same for ages, right? There are no surprises here at all. There is nothing new here. Everything works as expected. So we have byte counts 2 for everything, and then when we get to the complex points, we get 4 byte counts. That's it. So if you have been using nvarchar so far, you're fine. But you have varchar columns, then you might be able to benefit from the UTF-8 collation. Okay. Okay, so what's the most recent multi-byte language today? We are all using it. We are all using it on our phones. Emojis? Exactly, emojis. Or emoticons. So they have been defined by the Japanese in the early 2000s. In 2010, they made their way into Unicode. I don't know why, but the Japanese seem to be way ahead of these things compared to the rest of the world. When I was having this session in another country, they asked me, so why are they yellow? And a person answered, you can guess what. Turns out they're yellow because of contrast. If you had an emoticon, for example, which would be green, it wouldn't be as good as contrast and as it is when it's yellow. So it's basically it wouldn't give the person looking at it, it wouldn't give the same emotional response. So there's a kind of a science to it. So then we get to the code point composition. It's called code point composition, also known as what on earth is a character. And we'll take an interesting look at an emoji character. And this is a woman firefighter, medium skin tone emoji. That's the official name of this picture, or emoji. How do we make it? Any ideas? Yeah.
You take the base, which is probably yellow, and then you add things onto that, so you're combining multiple into one.
True. So what she said is you take the base and then you add things to that. True, very true. So what you do is you have 4 different code points. First, you take the woman emoji. Then, you take the emoji called the modifier Fitzpatrick type 4. Now, if you have ever done anything in dermatology, you know that the Fitzpatrick type is a skin color. It's a definition for the skin color, right? So skin color Fitzpatrick type 4 is a brownish skin tone. Type 1 is a very Scottish skin tone, right? And type 6 is very dark skin tone, right? So rendered as a square. It's not rendered as a square. It's basically a brown patch when it's by its own. So what you take is you take this brown skin tone and you paint the woman in brown. Then you take something called a zero-width joiner, which is used to glue, code points together into the same character. And then you take a fire engine, and then you glue the painted woman on the fire engine. And that, ladies and gentlemen, makes a woman firefighter. It's insane. So let's take a look at that. Okay, so here we go. And we're gonna do SQL for that. 5. So here we go. A woman, a brown skin tone, glue, and a fire engine. And it gives us this. It's not as pretty, but it is what it is. Now, what if we remove the glue? What will we get? Yeah, two things. A brown woman and a fire truck. So you need that glue. But what if we change the glue's position? No. There will be a woman, a brown patch, and a fire truck. So where you put the glue is very important, right? Okay. Okay. Then we come to something called the Unicode equivalence. Now, when you have text that comes from different sources, they can have the same characters, but differently composed, right? Basically, different code point sequences represent the same character. And this is used for compatibility reasons. This whole Unicode equivalence is used for compatibility reasons. So we have two types of equivalence, if you will. A canonical equivalence, which means they are exactly the same, and a compatibility equivalence, which means they're kind of similar. So the canonical equivalence means that the code point sequences are equal with appearance and meaning. Right? So they look the same, they mean the same. That's it. So for example, if you have an A with 2 dots on it, that's a one code point. But you can have it also as a Unicode code point composition with a normal letter A and 2 dots, which is its separate code point. And you put them together, and you get, again, the same A with the 2 dots on it. Right? Sorry? Yeah. Exactly. Yeah. Now, when we get to compatibility, it's kind of similar. It means similar meanings. So they can have possibly distinct appearances, but it's the same meaning in some contexts. Right? So you have to have the main knowledge of the text itself. One of these kind of things is the typographic ligature. I have no idea how to pronounce it, but it's FF. And its compatibility equivalence is basically 2 letters F. Right? So to show you this, I have created, so the SQL server, or T-SQL, doesn't have this built in. So I've created basically a CLR assembly. CLR has this on the string class. Okay, so we have A. Let's put this together. Okay. We have a typed character, which is A. We have a single code point character, which is, again, A with a umlaut. And then we have a combined code point, which is, again, the same appearance, same meaning. So this is this thing here. So we have A, single code point, and 2 characters as combined code point, right? Then, actually, just a moment. I should have shown you this first. So we have normalization for canonical decomposition, canonical composition, compatibility decomposition, and compatibility composition. Basically, characters are decomposed by canonical equivalence, and multiple combining characters arranged in a specific order. This means the canonical decomposition. So you take the A with 2 dots and you separate them. When you compose them, you put them back together, basically. And the same thing for the compatibility. So with the canonical composition and decomposition, you should have the same thing. But with the compatibility, composition, and decomposition, you won't. So now, let's take a look at this. Okay, so we have decomposition. So this is decomposition. This is composition. So back to composed form. And we see that we have here, we have decomposed it into 2 characters of 3 bytes. Why 3 bytes? A is 1 byte, 2 dots are 2 bytes. And when we go back is A with 2 dots, 1 character, and 2 bytes, which is again fine. Okay? So that's canonical. And this is the compatibility. Again, the FF ligature, single code point, combined code point. And this is not the same. And the same thing as before. It looks similar, right? They all look similar, which is the whole point. But if you look at the actual characters, it's the typed character is the ligature, single code point is again the ligature, but the combined code point is FF. And these 2 are again FFs. Now this comes into play if you have texts that can be old, and you have to kind of translate them into modern scripts, if you will. I'm not sure if Welsh has any of these things. I'm sure it does. As I was driving here from London, I was like, yeah, probably has. So all of these things are the rules by which all of these things work is called canonical ordering. So basically when you're doing decomposition, you have to put the things in the correct order. If you remember before the glue, you have to put the glue in the correct order for the code composition part. Same thing. Okay, so security issues. Anybody heard of the IDN homograph attack? Okay, so first we have to know what homoglyphs are. So homoglyphs are characters that look alike but have different meanings. So like 0 and O, or I and 1 in different fonts. So that's why sometimes you have passwords that are not, they don't allow like 0s and 1s and Ls and Is, right? And then you have a homograph, which is a word that are spelled alike but different in meaning, like a bow of a ship or arrow and a bow, right? Okay. So let me show you how this works. So I have here just like this. Microsoft.com, Microsoft.com, right? Nothing unusual about this, right? Yes? No? I can hear from the audience. Right? Okay, let's see what's going on. Let's put this here. Come on. Okay. So we have URL1, URL2, URL1, URL2. Here is 0, meaning it's the case expression. It seems they're not alike, although they seem alike, right? Why? Because a Latin O and a Cyrillic O, they look the same, but they're not. And URLs, they are also not the same. And we cannot see this with our eyes, right? Because the characters are the same, the font is the same, because we're using a Unicode database. If we change this to non-Unicode database, right? Because the Cyrillic O is part of the extended character set, it doesn't know what to show there, so it shows us a question mark, right? Okay, any questions so far? Okay. I really like these characters that they created for us, because they kind of fit into the theme. We're not done yet. So this is a feedback link, right? When I received this link, I received an email saying, please tell the audience to enter their feedback because it's very important to us, and it is, right? To me as a speaker and to the organizers, so they know if they want to invite me next year or not, right? The problem here is, when you go to that link, you can go and see for yourself, the text in red is what you get. It's not the name of the session, right? And that's why you need the sessions like these, right? Because if people from this website came to this session, this would not have happened, right? And if you put in some Cyrillic O's in there, you know, you can do a lot of damage. Okay, now we are kind of done. So if you have any questions, let me know. We have a few minutes left. It's once you get to deal. So we had a system in 2005, which was meant for English, German, and Spanish. And then in 2011, we upgraded that to 25 languages. It kind of needed a whole rewrite of things, because it didn't use varchars, it just used varchars. And then the UTF support came, and then they tried to just move everything to UTF, and that didn't work as well. Why? Because some columns had the 30-byte characters, and their space increased by 33%. And for the table, right, or for the column. And that space is not, I mean, space is cheap, but it's something you didn't think about when you have to test these things out, right? Oh, we have a question on screen. We don't?
It should show up.
Should show up. Where did those questions come from?
Virtual attendees.
We have virtual attendees? Excellent. I didn't know we would have them. Nobody told me. Excellent. So the question is, so should I convert all nvarchar columns to UTF-8 varchar in SQL 2019? Large customer. I need multilingual support, but nvarchar is wasting terabytes of space as mostly English characters stored. Several terabytes, few billion rows. Yes. Basically, what you do is, if you can, take, for example, since space is cheap, take 100 gigabytes of your data and convert that into UTF-8 on varchar fields, and see how much space that saves you. If that saves you a lot of space, then do it. You have to test it for like client compatibility and stuff like that, but if the question is just with the change, then I would go for it. Okay. Any other virtual questions? No? How many virtual attendees we have?
44.
44, cool. Okay, so to all of you, if you don't have any questions, and to the 44 people online, I wish you a great day. I hope you have a good party. If you think of a question, you know, while you're having a beer, let me know. We won't discuss it. We can do that tomorrow. Thank you. I hope you learned something and enjoy the day.